scene graph expansion using generative models of graphs. Creative photographers are gifted with the ability to imagine a set of concepts, objects, and inter-object relationships to capture in a photograph. However, they spend prohibitively expensive amount of time arriving at the kind of scenes that contain this set of concepts that they desire to be present in the photograph, and are often tasked with sifting through a large number of photos to zero in on the scene they want to capture. Hence, it is desirable to empower them with recommendations of a wide variety of diverse and rich scenes that contain these seed set of concepts. We wish to devise algorithms that can be leveraged to provide the user effective recommendations of scenes that subsume the seed concepts while ensuring they are diverse and richer than the seed concepts can represent. To this end, we express the seed concepts in the form of a scene graph and cast the task of producing richer and diverse scenes as generating of plausible novel scene graphs that subsume the seed graph. A majority of the scene graph literature is focused on generating scene graphs with image as input. However, different from this task, we want to focus on the underexplored task of scene graph expansion. Expanding scene graphs and retrieving or generating images that correspond to the expanded scene graph allows one to have at their disposal a wide variety of photos with the same seed concept. The closest to our work are Garg et al. CVPR 2019 and Verma et al. ICML 2022. So our proposed method GEMS works as follows. We take a scene graph, convert it into a sequence. The sequence is then expanded by our model. We convert the expanded scene graph back into a graph. While converting a graph into a sequence, traditional approaches apply DFS type algorithms. However, they work only for connected graphs. We observe that scene graphs naturally consist of clusters of objects, and thus running a naive graph to sequence algorithm would not be able to exploit this structure. Thus, we use a simple strategy called cluster-aware BFS, where we convert every maximal connected subgraph into a sequence and then concatenate sequences to get the sequence for the entire graph. While training, we compute a loss for the expanded scene graph S dash with respect to the ground truth expansion of the given seed scene graph. A naive way would be to use the cross entropy loss. However, we modified it using a class balancing term and a component which tries to distill external knowledge. Our source of external knowledge is embeddings trained using language corpuses and knowledge graphs. Here we show the design of our graph expansion model along with the inputs and outputs at timestamp I. As a first step, the model first uses v sub I minus 1 and e sub I minus 1 to generate a new node v sub I. And in the second step, it sequentially generates relationships between v sub I and existing nodes v1 through v sub I minus 1. The model continues doing so till it generates an end of sequence token, or we sample a maximum number of tokens. Here we show the impact of distilling external knowledge without going into the mathematical details. On the left, we see that the vanilla cross entropy loss is indifferent to the semantic meaning of the label. That is, the loss between orange and lemon is equal to the loss between orange and pole. On the right, when we use external knowledge, the loss now takes into account the meaning of the label. Hence, the loss between orange and lemon is less than the loss between orange and pole. We see comparison of expanded scene graph between method and baseline methods. We see that our method is able to produce more semantically meaningful relationships between predicted objects compared to GraphRNN. Our method produces denser relationships between objects compared to the baseline methods. Our method also predicts a diverse set of relationships between objects compared to GraphRNN and scene graph gen. We see comparison of results both for expanded scene graph and the corresponding generated images between our method and baseline methods. The images are generated using pre-trained sim